So hi, I'm Christophe. I've been using Postgres since 1997. I think my memory is indistinct. It was either 7.2 or 7.4 was the first version. The oldest instance of Postgres that I'm currently running is 7.4. I work with PostgreSQL Experts, Inc., along with Josh, who's the CEO in the back there. Hey, Josh. That's my email address. That's my personal tech blog. And that's my Twitter. I signed up for Twitter really early. I got an email, Twitter handle there. So what we're going to talk about today is, so what's a schemaless database? What is this thing I'm about to talk about? How can you can use Postgres to store the data? And how the various options that you have in Postgres for schemaless data perform relative to each other. So there's this term, NoSQL. It's really the worst term ever. And not just because I'm a SQL guy. Really, fine. You don't want to use SQL, that's fine. I mean, it's true that all the schemaless databases out there like Mongo, Cassandra, and all these guys don't use SQL, but neither did Postgres before it became PostgreSQL. Anyone remember Quell? No, I don't either, but anyway. But the defining characteristic of one of these things is a lack of a schema. So having just said that, what's a schema? It's a fixed, though mutable over time, definition of the data. So there's, in Postgres you have databases which contain schemas, which is a really unfortunate term since now we're using schema for two different things, to tables, to fields, columns, attributes. And you define that. That's it. That's the way the data is. You can have individual fields that are optional, like nulls, but adding a new column, you have to go and change the schema, and that requires a certain amount of pain. Sometimes an extremely small amount of pain, sometimes a huge amount of pain, but the pain is never quite zero. It may asymptotically approach zero, but it's never zero. So people didn't like that because, SQL was your dad's database. And so along came schemaless databases, which store these. I'm going to adopt the term document because that's the Mongo term. They don't like the term rows because, rows are spreadsheets and only boring people use spreadsheets. They have internal structure, but that structure, there are no fields, there are no schemas. You make up whatever you like. It's great. As an old data guy, this is kind of like, you've got to be kidding me. It's like, this is my nightmare. It's really different from the old glasshouse model, where you had the priesthood who managed the schema, and if you did the right rituals, you were allowed access to the data that you put in there. Largely, these schemaless databases grew out from the people who were writing things in Python or Ruby, on Django or Rails. And I'm a Django guy. I love Django. And they needed to cram this stuff into a database. And then someone came along and said, great, but then you have this mapper and you have this and this, and you map it to that, and that doesn't quite work, and this doesn't work the way the object is. And everyone went, you are so old and in the way, and came up with a whole different data storage technology to handle this in the form of schemaless databases. So, VSAM, it's like, all technology is cyclical. But, however, and that's all I'm going to say about the cultural aspects of this, because we can rant forever about this, and after a while it gets pretty tedious. But let's not talk about this stuff, because that's not, we're technical. This is a tech talk. So here's what I'm going to focus on. You want to store schemaless database, and what you've got is PostgreSQL. What can you do? What are your options? And in terms of performance, what can you expect? So what's schemaless data? It doesn't mean unstructured. What it means is it's generally a hierarchical structure of arrays and key value pairs. JSON objects are kind of the example these days of this kind of data. The application kind of does have a schema in mind because when it gets one of these things, it has expectations of what's going to be in that. And if you don't meet those expectations, generally bad things happen. Or at least it reacts in some positive way. Here's hoping. The good news is we've got all sorts of ways of storing this kind of stuff. We have 3 separate types. We have XML, hstore, and we have JSON. This talk is as of 9.2. So let's see what we've got there. So XML. You might say, being completely unbiased here on my opinion of XML. So it's been around since the mid-90s. It's hierarchical data structure based on SGML. It's, for a while, XML, remember XML databases were going to destroy RDBMSs and we were never going to hear about them again? That lasted for, the tech press got a good 2-year run out of that one. SOAP and all these other things are based on it. There's still tons of XML out there in the real world. In the Java world, it's super popular. And it is kind of, your dad's document structuring language. You can use these DTDs to specify the schemas. No one really does this. I mean, right now, there's a clock that's ticking about once a minute for every time a DTD is actually checked somewhere in the real world. And then you can do these automatic transformations using XSLT. Everyone ever try writing XSLT? That was one of those about 10 minutes. It's like, oh, you've got to be kidding me. Only masochists do this stuff. However, XML is extremely important for one thing: Tomcat configuration files. This is the primary use of XML now. Okay, so XML, but if I haven't talked you out of XML, we've got XML and Postgres. It's a built-in type. It's actually been around for quite a while. You can have documents up to 2 gigabytes. That should probably hold you. There are a lot of XML operators, too many to list, as they say. The most important one, which we'll talk about extensively, is XPath, which is the path language-based subdocument extractor. So you can write these path expressions to get pieces of the XML tree out. And some really actually very nice XML export functions for exporting the databases, XML, and things like that. Interestingly enough, XML just crops up in the weirdest places, like Django's object serialization framework uses XML as its primary storage technique. So, when you least expect it, it pops up. And lots of places do have external XML requirements. A lot of these corporate message passing systems that are very popular as middleware, middleware is sort of the generic name they use for the technology. A lot of those are XML based. And so if you have these XML requirements, it's very handy to have this as a built-in type in Postgres. So the problem with XML in Postgres on indexing is there isn't any. There isn't any special built-in indexing for XML. You can use an expression index, which we will do in a little bit, and see how that works, using XPath or one of the other operators. The functionality is great. You can do all sorts of fancy things and build these really fancy indexes with it. The performance, we'll talk about. So, hstore, which is in contrib, it's not a built-in core type in Postgres, but it's in contrib, so it's part of the standard distribution. It's a hierarchical storage type that's specific to Postgres. It was interesting, but kind of for a long time, and then a 9.0 that got, or 8.4 or 9.0, I forget which one. A lot of work was done to it to make it a lot more flexible. It's really nice. It's basically a hash, like a Perl-like hash. You map string keys to string values or to other hstore values, and bang, you now have a hierarchical type. It's a contrib module. It's not part of the core. There are lots and lots and lots of cool hstore functions for doing all the usual stuff, like does this key have this value? Is this in here? Adding and subtracting keys from the hash, things like that. Using Postgres' ability to find their own operators, so you can write code that looks like line noise, and all sorts of stuff. There's a lot of functionality in hstore, very well documented too. The good part about hstore also is you get gist and gin indexes, and we'll talk a little bit about what those are if you're not familiar with them, over hstore values. So you get built-in indexing on these. What's nice about these is they index the whole hierarchy of types, not just a single key. So you don't. So you get the whole thing is indexed in these indexes. There's a price for that, but you do get it. Accelerates these operators, which are: is this key there included? Does this key exist in this hash? Do any of these array of keys exist? And does one of these array of keys exist? Those are in the docs. And you can also build expression indexes, of course, because you can build expression indexes over anything. So JSON, brand new as of 9.2. JavaScript object notation is what it stands for. It's basically JavaScript's data structure turned into a protocol. They sort of like blessed it and said, okay, this is it. It can contain dictionaries, so hashes again, arrays or primitive types. And originally it was designed that its super clever fancy parsing was you took the thing, dropped it into the eval function in JSON, it would parse it and run it as a JSON program. Please don't do that. That's like, we just got to, it's like, I hope a moment would reveal the security problem of just running arbitrary code here. Yeah, well, there's that too. So REST web services, basically, they're all, when anybody who's like, under 30 is writing stuff using JSON now. It's very comfortable. Python and Ruby programmers like it because it looks basically like the data structures they're used to. MongoDB, it's the native data storage type. And the good news is, JSON's in core as of 9.2, JSON type. It validates the JSON going in, so you just declare a field as being JSON, and you drop it in, it'll tell you if it's correct JSON or not. And that's pretty much all we got right now. Sorry about that. We do have an array to JSON and row to JSON functions. Lots more coming in 9.3, hopefully. Not yet committed, but. JSON indexing, back to using expression indexing. You can also index it as a text string. So for strict comparison, I have absolutely no idea what use this is. Kind of weird. I guess for really simple structures that might be useful. But anyway. But the coolest part of having JSON in core is PL-V8, which is the V8 JavaScript engine from Google embedded as a PL, embedded programming language inside of Postgres. As you might imagine, JavaScript kind of deals well with JSON, is sort of what it's all about. And it's not, unfortunately right now, this is not part of core or contrib. You need to build and install it separately as an extension in Postgres. Having done this, allow me to pass on some words of advice. You need two pieces to make this work. You need the V8 engine, and you need PL-V8 to glue it to Postgres. The PL-V8 download comes with V8. Use that one. Otherwise, you will spend hours and hours and hours dinking around with it. I have no idea what the guys at Google has used to develop this thing, but whatever it is, it's no computer I've ever seen. Because I'm not sure what the development environment for this is, because none of them seem to work very well. A note that the first time you use a V8 function, it's compiled by the just-in-time compiler, which is cool. So it's not compiled over and over again, but it does have to be compiled once. That means also the first use is the first time it really checks the syntax of it, not when the function's created. And yeah, about that eval, now that we got rid of all these SQL injection attacks, now we have to worry about JSON injection attacks. So use the safe parsing methods for JSON. Don't use eval. Also, the overhead to invoke a PL function is not 0. It is, you will feel this. So this does matter on things like expression indexes and the like. So we've got this stuff. What do we do? What we do is actually pretty straightforward. You can create a single field table. This is the most reduced case. You want to treat Postgres as a pure schemaless database. You just create a single field table with only one column, which is the hierarchical type. There's really simple SQL you can use. Sorry, can't be pure NoSQL, but that's okay. To provide an object API. And you create indexes to taste as necessary. And if you maybe you may want to extract fields if you need to join on them. You could write a trigger that populates other columns if you want to do joins. And you're done. That was pretty easy. So, for example, here's a little JSON function, PL-V8, that pulls one key out. This will be built in soon enough, but for right now, you get to write in PL-V8. Provided by Andrew Dunstan, a colleague of mine who spent a lot of time working on V8. PL-V8. Ta-da. And then you create your table. And then you say, okay, well, let's say this is the primary key. Of course, we don't call it that because now we're in the new world where there isn't all these relational things like primary keys. But you have a post ID or something. And you get the key and you cast it to begin and you create an index on it. Expression index, you can tell because of the double parens. And then you say, well, okay, but we also want to index on timestamp. Now, trick question. This will fail with an error. Why? Josh does not get to answer. Anyone know why this is wrong? I left it in, when I was debugging the slides, I left it in. Nope. Sir. You can't because casting to timestamp CZ is not immutable because of time zones. So you have to do something else here. Left this exercise to the reader. But you get the idea. I left it in because it's kind of, this trips me up every single time. You know, I keep forgetting that. Anyway. So you say, well, okay, Christophe, that was great, but I've done all this work, but this is not what Postgres was designed to do. I mean, you're kind of forcing it into a role here. Why don't I, you know, apt-get install MongoD? Huh? You know, maybe that's an easier thing to do. Well, let's find out. So how does this perform? You know, when all else fails, let's actually run some numbers. So we're going to take a very basic document structure, which has ID, name, company, address 1, address 2, CSA postal code, basic US address mailing list. Address 2 and company are optional fields, null in the relational version. And the ID is a 64-bit integer, and all the others are text. Sweet. And 1.78 million records, because I happen to have a big mailing list lying around. So we're going to compare the traditional relational schema, hstore using just indexes, XML, JSON, and for these guys, 1 column per table, and MongoDB. I wrote some scripts in Python using PsychoPG for the Postgres interface and PyMongo for the Mongo interface. And the test track is this laptop, just in case anyone, you know, never came close to using all that memory, but, you know, blah, blah, blah. It has to run on some machine, you know. So the indexing philosophy. So for the relational, I just created an index on the primary key. For hstore, I created a just-in-gen index on the single column. For JSON and XML, I created an expression index on the primary key, pulling it out using expression and that. And for MongoDB, it declared an index on the primary key field. And I created the indexes before the records got loaded. So the load times you're going to see include index creation. So my methodology sucks, and I'll tell you why. The documents aren't particularly large. There are no deep hierarchies, and the key space is kind of limited. I ran everything repeatedly to keep the cache hot because otherwise you get into, you know, guaranteeing a cold cache is kind of a fool's errand. There's only one index, and there are no joins. So I think these are representative results anyway, but, you know, I like to anticipate all the various criticisms that I could. Oh, and I didn't do any updating. It was read the thing, do the queries. So in short, you can build a workload that shows something completely different than this one. I guarantee you. So my sophisticated database tuning technology was I didn't do any. It's a stock PostgreSQL 922 from source, built from source. Didn't even touch PostgreSQL.conf. It's exactly as it's installed. Stock MongoDB 2.2, that's a little less radical because Mongo's not a heavy, you know, you're not supposed to configure Mongo. Just fire it up and let it go. Okay, the first test I did was let's get these records into the database. So it read a CSV file, parsed into appropriate format, and inserted into the database. Droop. So we measured total load time, including the time the Python script was running doing the parsing. I did inserts for Postgres, not copy. Copy would be much faster here. But I wanted to do the pick up a record, stuff it in, pick it up a record, stuff it in. And Mongo import, the equivalent for Mongo, would probably be much faster also. Ta-da! Some numbers. Higher. This is records per second. Everyone stands up. I love it. This is records per second. This is pure relational. This is hstore no index. hstore with a just index, and hstore with gen index, XML, JSON, and MongoDB. Higher is better. This is in records per second. Note it. So working, you know, relational was the fastest, followed by hstore. Index build time was obviously significant here. XML was not that super performant. JSON was pretty competitive. It was close to, it's actually a tiny bit shorter than hstore, but you can barely see it. And MongoDB was kind of in the middle, you know. Interesting. So I didn't make any attempts to speed up Postgres in this. It should be noted. I didn't do synchronous commit. I didn't tune checkpointing. I didn't do any of the things you know any intelligent person would do. Gin indexes are really slow to build. Yeah, it says so in the documentation, but they really are. For probably where it's spent, the XML load is probably spending its time is in the XPath function. I didn't go in and actually trace it, but because otherwise it should have been roughly about the same as JSON. So that's where I'm blaming the time. So disk footprint. So we've loaded all this. So I just used the reported sizes from the various PG size functions and DB stats for Mongo. Bonk. So relational's tiny. hstore, the data size is the same, but you know, gin indexes are big. Unsurprisingly, the index size on XML or JSON is the same as relational because it's basically the same index. It's just built differently. Let the record show I did a repair on this just because I didn't believe it. But no, it really is there. It really is that big. Yeah, gin indexes are really big on disk too. It says that in the docs too. Yeah, its relational database storage is actually quite efficient. It's only about 2 times bigger than the CSV file. It's kind of interesting. Notice that none of these records are toastable. There aren't any big things in them, which would probably hurt database the efficiency quite a bit. Yeah, MongoDB sure likes its disk space. And the padding factor was 1 also. Just no, I did not monkey with anything. I'm being fair here. So, okay, data's there. Query on primary key. So grab the sample of 100 documents. Grab the single document based on the primary key. I didn't actually fetch the results over the wire. Both Mongo and PostgreSQL's wire protocols, the query returns an acknowledgement, but it doesn't actually send any results back. So I did not do the results step. So I just timed the .execute from Python or the .fetch. Bonk. So there's a wide distribution here. Here's hstore, hstore gist and gin, and these. In fact, this is like so smushed up. This is like chart junk. So let's break them into pairs here. Here's the fast one, the fast group. So we have relational, XML. JSON's actually faster than relational. It's weird. These are kind of within noise of each other, though. And MongoDB is faster, is definitely slower. Almost a factor of 2 slower than these guys. The slow grouping, we have hstore, hstore with gist, hstore with gin. This test is extremely unfair to gist and gin, and I'll explain why later. Because I was confused by these results, so I did a little more analysis. But first of all, this being slow is not terribly surprising because effectively you have to do a sequential scan because there are no indexes. The fact that these are only down here, though, is kind of interesting. So keep these in mind. So B-tree indexes kick ass. You know, they are just the right thing for if you are retrieving a single distinct value. Gist and gin were surprisingly slow in this test. The relational XML and JSON are interesting, but they're really not statistically significant. I think that has more to do with just random noise than anything else. Yeah, and you know, Mongo was supposed to blow the doors off of everything else. Interesting. Okay. Query on name. So grab 100 names, query all documents with that name. The results are not fetched. This requires a full table scan except for hstore because there are no declared indexes for everything else on name. Same time and methodology. Bloop. Well, my goodness. They certainly have 2 groupings here. Yeah. So let's, again, we have two clusters. Gist and gin basically ran just as fast. Because the nice part about gist and gin is they are indexing the whole field in one index, not key by key. hstore for doing a full table scan was slower, and relational fast, and Mongo was not so great. It was okay, not so great. The slow ones, XML was really slow, and however JSON was, well, 4 times faster, but that's not much to So, The good part is just in Gin accelerate every field, not just the primary key. You know, using these accessor functions is really slow because it's having to process this accessor function on each row to determine set membership. Yeah, the problem with MongoDB is it's just a bigger file, and it has to read a bigger file doing the sequential scan. Not that there's anything wrong with that. No value judgment here, that's for sure. Okay, so now that we know that, what do we know about this stuff? So performance-wise, Postgres did pretty well as a schemaless database. Using built-in indexes on commonly queried field or just in Gin and hstore if you want full flexibility. So avoid doing full table scans if you need to use an accessor function. Index those things because it only has to process the accessor function once, and then it can query the index. Executing that accessor function for each row really kills performance. hstores aren't as bad as XPath or a PL. Part of it is that XPath really has its own little programming language built in there. I don't know if it's Turing complete, but it's awfully close. And that has to get compiled and run, so that's going to be slow. And there is some overhead bridging to a PL. If you have the flexibility, that is to say you can build whatever schema you want, seriously consider using hstore because the performance is really quite good, and you want this kind of blobby data. It's fast. So Gist and Gin, which are two indexing techniques built in Postgres. So the question is, why did they suck so badly in this test? I would have expected them to be much faster. So I did some analysis. In general, they don't suck. It's just that for this particular job, they were not the right choice. This test has a very small key space and relatively similar data, row to row, because it's a mailing list. Things are roughly the same size. They're all Latin 1 names. So Gist and Gin perform better the more entropy there is in the data. The less similar the various rows are to each other, the better these two perform. As the data size increases, Gin will generally outperform Gist as data size grows because of the way they're designed. This isn't primarily an indexing talk, but just to go, Gist is a B-tree index. It's a generalized B-tree index. It effectively takes a hash signature of the, in the case of hstore, of the row and indexes that. Gin is an inverted index and was primarily designed for full text search. It actually takes a list of every key and every key's value and then builds a B-tree index for each and every one of those showing which rows contain it, which is, you can imagine why the thing's so big. It is, however, extremely efficient. For example, I did if you do a check on Gin using the Gin index for, give me all the rows that this key exists in, that's extremely fast. On this data set, it's like 35 milliseconds. So that Gin is very good for answering those kinds of questions. Not so great for these generalized get me key number 85 questions. So again, Gist is good when the records have a lot of entropy because there are fewer hash collisions. Things generally run better. Gin is better for highly variable key sets. So record to record, the keys are not that similar, like they are in full text search. Like full text search meets this, and you generally query on key existence rather than is this key, get me PK85. So here's the flame bait on this talk. It doesn't seem Mongo did not seem to be more performant than Postgres. I'll just say on this based on this test, and you get all the Postgres goodies. So, larger documents will probably continue to favor Postgres, based on the reason what's going on here, and larger tables as well. That being said, you can find a workload that proves anything runs well. I mean, I could probably come up with one that shows DBase2 outperforms Postgres. So be realistic about your workload. Use real life data now and in the future. If you're planning to grow by a factor of 30, test with a factor of 30 data, not with the current set of data. And what I just said. test with real world data, because all these tools are highly sensitive to the particular distribution of data. And that's my talk. Questions? Mm-hmm. Right. It's just that a value can be another hstore. Mm-hmm. Mm-hmm. Um, it doesn't have it. There's no built-in structures that do like that like have built-in visit or something like that. That would be really easy to write, though. You know, in PLPGSQL or something like that. It's very easy to like extract and then call again on the child hstore, things like that. But there's no like visit function built in to it. But it'd be a really easy thing to write in PLPGSQL or something like that. Did that answer the question? Okay. Well, in the sense of like a function that will call a function for each node to descend. If you want to like walk the tree of this, yeah, that would be very easy to write there, but there is not a built-in function that does that. Or in PLPGSQL or some other built-in PL. Sure. Postgres is very web scale. Mm-hmm. Well, wait. Every time you commit, not every time you insert something. Yes, yeah. So they were so they were done every single transaction. Yes, the insert performance would be much lower if I committed at the end of each at the end of each one. But of course, if I turned on, unless of course I decide, at the point I'm tuning, I could do a lot, But no, the whole things were inserted in one. Of course, at the end of the commit, it also has to do at that point, it does have to flush everything to the wall. Also, the wall buffers in memory do fill up. So it is spilling things to disk during this. It's not keeping the entire thing in memory and then just slamming it on at once because, you can insert as much as you want. So, sure. Well, it's not safe in that sense. It's safe. But they do have a right. They do have a log. I mean, fair is fair. They do have a recovery log and things like that. I believe that they are as safe as the underlying medium to a crash, even in the case of a single node. I believe that's the claim as of 2. Well, I believe somebody correct me if I'm wrong, but my understanding is they claim to be crash safe as of with single node recovery. Obviously, if you lose the underlying storage, that's a problem. But I mean, happy to trash Mongo, but I don't think that's correct. But I could be wrong. I'm not a Mongo guy. Anything else? Yes. Well, the relational test was one column and nulls for the missing fields. Well, that depends on what key value technology you're using. That's kind of what the hstore and the JSON and all those guys was a single row. Okay. Well, in the sense that I'm not quite visualizing the structure you're proposing. I guess, if you have a key value, do you mean like a multi-table key values, like an entity value store where you have like address, like one column that's the key and one column that's value, so it'd be address 5, address, primary key, something like that. Mhm. 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 Well, sure you could. Well, in Postgres you can. You just declare an array type. Yeah. Hmm. Right. Okay. That's just right. What another term for what you're talking about is an entity value model, which is entity value. Yeah. Generally, those perform really badly. You know, that's you know, there are times you need them. You know, it's you know, never categorically rejected entire technology, but the problem is it has to do a lot more gathering of these things. That, you know, it has to pull everything in to, you know, pull in multiple rows and grab them together. If you are in it, I think these days I would be more inclined to use hstore or JSON to do that kind of, you know, that kind of structure. Or if all I needed was a multi-value, a single column that had, you know, could be 0 or more things, I might use an array instead of that, since Postgres supports array types very nicely as a single value. And, you know, really super hardcore relational people go, oh, gross, arrays, that's horrible. But, you know, they're the right answer for some of these problems. You know, it's there. You know, you can look at it. You know, you can sort of play the, you know, like that old the old children's book they used to teach French. Fortunately, unfortunately, you get a Postgres and Mongo knocking back and forth. It's like, well, but you know, Mongo, you have to suck in the whole document, and then you know, I'm sure you can come up with a good response for Mongo for things like that. Mostly, I think the core takeaway from my talk is you're not destroying. You know, you don't have to race to a separate technology just to get reasonable performance, even if even if your problem is well solved by schemaless data. Hadoop. Well, I guess Hadoop runs on HBase, but there are plenty of, you know, there's nothing in the core product that's a MapReduce function, but you know, there's nothing particularly this is, I think, a little bit of a sleight of hand. It's like the web scale thing, you know, as they say, like, well, is that saying, you know, MapReduce is not a relational versus not relational technology, you know, essentially, you know, it operates on things. That thing can be stored anywhere.